In this video, we're going to talk about protecting against catastrophic shorts, why some fuses explode, and why that's bad. We'll use electric vehicle battery arrays as an example, but this can apply to any situation where high voltage, high current shorts are possible. Now, what do we mean by catastrophic? Well, just watch. That is not how a fuse is supposed to work. With EV battery arrays, you have the potential for high voltage, high current short circuits to occur, especially after an accident. Inadequate protection puts passengers and those assisting at risk of fires or explosions from these shorts. It's a typical application for the seemingly simple wire and air fuse. But the video you just saw shows that maybe they aren't so simple. And the point of the fuse is to prevent fires and explosions, not be the source of them. Inside the battery enclosure, you will typically find a circuit board connecting battery cells with the battery management system, with an array of wire and air fuses intended to protect against overcurrent events. In rare but very real circumstances, like after a collision, the sensing cables could be shorted, and these fuses that typically handle half an amp or less could be exposed to very high voltages and currents. Test boards, like this one, are used to characterize how circuit protection devices on the connecting circuit board react to these extreme events. The video clip I showed you in the introduction used this kind of test board. So let's look at a conventional wire and air fuse. These use a typical passive footprint with case sizes of 2410 or 1206. Inside you have a wire suspended in air between the two terminals, and at the terminals you have a couple of solder joints to hold it in place. In this case, the wire isn't well aligned, and you'll see some variation in its alignment. Poor alignment can allow the case to act as a heatsink and affect the time it takes for the fuse to open. So what can happen with these fuses? Let's see. Again, this is a problem. You saw the fuse blow, but then it continued conducting, likely due to prolonged arcing caused by the solder used in the cavity. And then it finally opened. These fuses go inside battery packs, which are sealed to keep out fluids and other contaminants. A fuse exploding like this would likely break that seal, or break the seals on the batteries themselves. In either case, leading to more potential shorting or ignition of the battery pack, which would be a much larger fire. AEM Components has taken a different approach with the construction of their air matrix wire and air fuse. Rather than dropping the wire and soldering it in place, the fuse element protrudes both ends and is externally fastened to the terminals. This leads to much more consistent, straight placement of the wire in the cavity, and the solderless construction eliminates the secondary conduction and subsequent failures that you saw with the conventional construction. The test was actually conducted at 450 volts and 400 amps, and the fuse did its job. We can see this in the scope shots as well. With air matrix, we see the rising current, then the fuse blows and the current drops to zero, and you see the voltage rise across the now open fuse. With conventional fuses, we see the fuse blow, but then it doesn't open completely. Additional conduction paths are formed by the arcing, allowing current to keep flowing until the fuse finally opens and does so violently. Again, this places anyone in or around the vehicle at risk. We've highlighted some potential risks and issues with fuse selection for high voltage, high current applications, like PCBs in EVs or power storage, and shown how the construction of air matrix fuses yield consistent, reliable performance even beyond their datasheet rating. For more information on air matrix fuses, visit aemcomponents.com.